we're going to talk about Coulombs law, and Coulombs law can help us calculating the force between two charges. A charge is when we have too many or too few electrons in a place. For example, a battery, we got a positive terminal and a negative terminal. On the negative terminal, we have many electrons. We have too many electrons in accordance to neutron. And the positive terminal, we have too few. But the charge can be everywhere, also in the air. So it just depends on the number of electrons in an atom, for example, and normally we got many of them. And here we got a positive and a negative charge, and we're going to calculate the force between the two charges. We have the distance between the charges. Up here we call it radius, but down here in this formula we just call it the distance. So the force is a constant times the charge of one load and the charge of the other, and divided by the distance squared. Now we're going to know the charge Q. We can see it has the letter Q and it has the unit coulomb. And 1 coulomb is 6.242 times 10 power to 18 electrons. So that 1 coulomb is very many electrons. And 1 coulomb is also 1 amp times seconds. So 1 coulomb is the same as 1 amp second. It means that if we got a wire conducting or leading a current of 1 amp, for every single second there will pass 6.242 times 10 power to 18 electrons in the wire. So back again to Coulombs law. We have that the force was a constant multiplied by the two charges divided by the distance squared. The constant is 1 divided by 4 times pi times epsilon. That's a Greek letter. And epsilon is the permittivity for a given situation. And the permittivity is split into permittivity for vacuum, or just if we got free space, no electrons or atoms at all, and then multiplied by relative permittivity depending on the material between the two charges. So if we got vacuum up here, it means no air, no nothing. We have this number, but normally we have to multiply a factor or relative number depending on the material between the two charges. Epsilon 0 is calculated down here, and it is 1 divided by lowercase letter c, 0 squared, multiplied by the permeability. The permeability is actually the conductance for magnetic fields, and it is also in vacuum. This number is 4 times pi times 10 power to negative 7. Lowercase letter c, 0, is the speed of light in vacuum, and it is 299,792,458 meters per second. We have to square this number and multiply by 4 times pi times 10 power to negative 7. It gives us a number of 8.85 times 10 power to negative 12. So that's the number for epsilon 0. And it is the permittivity, and the unit for this one is farad per meter. We also can say that it is Coulomb squared divided by Newton times square meter. It is because if we take this formula, basic formula, and we want to know the unit for epsilon, we just can change epsilon and the force. the permittivity and the force, we just change it. So we got the unit for permittivity, we got Q, that was Coulomb, and Q times Q is Coulomb squared. And down here 4 pi is just a number, but then we got the force, it is in Newton, and the distance is in meter, and we have to square it, so it is square meter. This relative number for permittivity is depending on the material, and for example for air we got the number 1.000536. This should be a dot instead, so 1.000536. It's nearby 1, so we can see that it doesn't change the force very much if we got no air or vacuum, nothing at all, or just air. But you have to put in a number in the calculation. The force up here can be both ways, and we can see over here if the charge of the two is positive and negative, or negative and positive is different, and then the forces, they'll attract each other. Otherwise, if the charge is the same, they will repel each other. So if it's negative both of them, or positive both of them, they will repel. And it is because the lines between the positive charge here and negative charge, we got some electric force lines. They work together in this situation, so they will attract each other. We can see here that the positive charge has that the electrical lines, field lines, go away from the charge, and to a negative charge, the electrical field lines go towards the charge. It's similar for magnetic fields, but we have to remember that for the electrical charge, there doesn't have to be a negative charge to a positive charge and reverse. We have that for a magnet, that you have a north and south pole. You have to have both. But for electrical charge, we just can have a positive charge and no negative charge. And also we have to remember that this illustration is only in 2 dimensions, but in real life this happens in 3 dimensions. So these electric field lines is very difficult, and there are very many of them in the air, for example. So we just look on one example how to calculate the force between 2 charges. So that's the basic for Coulomb's law. We can calculate the force between 2 charges, and we just have to know about the 2 loads, the distance between them, and the relative permittivity, and then we can calculate the force. If we put in SI numbers, we got out in SI numbers and then we got the force in Newton.